on this computer. Okay, and then I will start with this presentation. So let me see if I can move this out. No. Okay, I think this will work. Okay, so first of all, thanks again. Thanks everyone. I think the official participation list is like 75 people. So that's really a lot. So I'm really happy because of that. I'm motivated, definitely. And the idea is that, as I said last week, I sent a reminder, I think 2 hours ago. So if you didn't receive it, it means that I didn't have you in the list, so I didn't include you in the list. So just send me a direct mail, and then I will include you. Or if you just join the course but you forgot to tell me, just let me know in later when you have time. Okay, so then I think we can start. Today is the second day of the course. I would like to start with the outline of what I will try to show you today. The first thing we will do is to starting to get familiar with Hsra, and we will do a synthesis. And also we will cover what are the input files that you need for running Hsra. And the important thing here is that I remark again that they are basically the same files that you would need in the future for design. So as soon as you get comfortable with them and you understand what they mean and how to change them or how to make new ones, then you are gaining the possibility of running Hsra, but also design. Okay, so then I will show you how to run it and how to do some simple things through a script of IDL. I think it's very easy, so probably those of you that prefer to use Python, it will be very easy for you to just translate it. But if you have problems or questions, probably either Ricardo or someone else that they are already using Hsra, they will probably have routines in Python to do everything that I will show you today. But my target is to show you how you can do things. The idea is that if you allow me, I would like to just go through different parts. It's not going until the end, but at least I will cover some parts. And then I will finish that part. And if you have questions, then we can cover them. But if not, just let me go through it. And the idea is that I will share with you, I hope, if you agree, every time we finish the class, I will send you all the files that I use during the class. So then you can run them, you can check them after the class. So with your pace, without the rush of trying to follow me. So just during the class, focus on what I'm saying, and then you will have the video and all the material. And then later on during the week, you can run it in your house or in your work with your pace and with no hurries. And if you have questions, then you just put them down or just send me an email or use the Discord channel that I think it was, I think it's been fruitful because people are sending messages with errors and we are answering them. So I think it's working well. And it's basically that. I think we are starting a community where some people know a bit more and some people are learning. But the idea is that together we probably can learn from each other. And I think by the end of the course, we will have a lot of experts working on this and we will be able to help each other. So I think that's very good. Yes, so then I will run the class and then I will try to send you some homework. It's not going to be too much, but just something that I would recommend you to try to just check if everything that I said today, you understand it, understood it. So, okay. This is a folder where I have a folder somewhere. I think it's here. And I put it some files. So I will share this with you. And the idea is that I put ideal routines for Hsra that I use in this program I usually use. I think they are almost the same or the same that you have in the GitHub of Basilio. But if not, you can copy them. They are basically doing the same, but probably I'm an older user of Hsra. So I'm using Hsra much before than 2017. So I probably have routines that are older than that. And the idea is that we will basically focus on this script that is called synth.pro. And I will show you what it does, and then we will check all the input files for Hsra that they are in this folder. So let's start with just this file, this synth.pro, and I put several things. So let's go one by one. And the idea is if I run it, now we have a stop here. And ideally, it means that the program will stop here. So it will run just until this point. So if I just run it, it will just run, it will do a synthesis, and it will show this profile. Okay, so now I will go step by step, checking what we need to do for doing that. So from going from a call to Hsra, and then obtain a profile. Okay, so then the first thing is that this spawn is a command for running Linux commands from IDL. So the important thing is what is inside this comma or tilde, and is that it's calling the file synth.troll. It's not because Basilio likes RPG or things like that. This comes from control. So this is the control file that commands Hsra. And then it's saying that you run this control file with executable inside this folder. So this is the source code that I send it to you. So if you compile it, then it will create this executable inside. And the idea is that we are just telling Hsra that should run this control file. Okay, so then let's go to that control file that is here. And you will see that it has a lot of sentence and an input. And these, you have, I think, the explanation on the manual, but at least let's cover the main ones for running synthesis. So the idea is that the code is an inversion. The code is an inversion code, so it was thought to always run cycles for performing inversions. So the idea is that when you run inversions, here you will have numbers larger than 0, 1, 2, 3, or 5. But for synthesis, you just put 0. Okay, it's also explained here. Then these profiles in the synthesis case are a file that you will create. So in the synthesis mode, you have an atmosphere. You will run the code from that atmosphere with a configuration file, and you will create a profile file. That it will be the one, for example, that you're seeing here. In the case of inversion, it's the opposite. In the case of inversions, you have a profile that you want to fit, and this will be your input file. But in this case, it's working as an output. Just one comment. Basilio, if I say something wrong, just let me know. Okay. For synthesis, I think we can skip these 2 lines. I will cover them when we are doing inversions. And then let's see this file that is called wavelength grid. So it's the first one that we have to define for the synthesis. And let's see how it looks. Okay, so we have here this wave grid file. And for this example, I configure it this way. So you have, it says line and blend indices. So I put it 6 and 7. Okay, these will be the lines that are in your line list. So they will have an index. I will show you in a moment. So they will have an index. And then if you want to synthesize a given line, then you have to put the proper index. The idea is that if you put just one index, for example, let's copy this below. So if you put like, I don't know, 5, it will be just one line. But, oh, sorry. Yes. Well, you can see it. So if you put like 5, it will be just one single line. But if you want to have a continuous spectrum and having 2 or 3 lines, the only thing that you need to do is to add the lines in the same, the indices in the same line. So for example, 7, 8, 9, 10. So if you have lines that are close together and you want a uniform spectral coverage, including all those lines, then the only thing you need to do is to include them here. Okay. So in this case, I'm synthesizing two lines that they are 6 and 7. So let's go 1 second to the line list. And you can see that there's some numbers here. Those are the indices. And what I'm synthesizing is line 6 and 7, that are the famous 6301 and 602 line. So they are so close, only 1 Armstrong difference, that usually we prefer to synthesize them together. Okay, so then let's go back here. So we are synthesizing 2 lines and with a uniform spectral range.
Huh? No.
Is there a question? Oh, okay. So then you have to specify what are the properties of your wavelength range. So in the first case is the initial point. In the second case, it will be the spectral, the initial wavelength, then the spectral sampling, and then the final wavelength. I think someone has a microphone on, so maybe.
I guess Sebastian.
Okay. Okay.
I'm so sorry.
No, it's fine. So then these are in milliarmstrong, and the idea is that the code will compute a spectral range referred to the line core wavelength of your index. So in this case, it will be the first index of the blend, so it's 6. So then when you said, I want to compute from -500 milliarmstrong, it will be compared to that, to this wavelength, okay? So I will explain this a bit in detail later, but the idea is that photospheric lines, you can start with probably -500 to 500 or -1000 to 1000, and probably you will cover the line. But this is something that you will see later.
Okay, just one comment to clarify. The wavelength range is the reference is the first line.
Yes.
Okay, it's in millions respect to the first line. You can.
Yeah, I think I lost Basil.
This is the case for 1500 because you need to go to the second line. Okay.
Yes, yes, yes. Sorry, I lost the connection, but. Sorry, I lost the connection. It's not good if you're the presenter. So, Basilio, I didn't hear you, but I assume that you were explaining that the wavelength range is referred to the first index, right?
Right.
Okay, okay. Yes, yes. And this is what I was going to say, that I said from -500 to 500 is probably fine. But as I said here, the difference between the two lines is 1 Armstrong. So then I'm telling the code, please go up to 1.5 Armstrong from the line core of this line. So then we can have this field of view that you have here. Sorry, field of view, spectral range that we have here. So as a note, I recommend you to try to use integers. So if you start from -500 and your step is 10, I think if you do this, the code will just try to reach us closer to this one, that it will be 1500, but it will not reach 1505 because it's a steps of 10. So, but Hsra will not complain about that. It will just give you what it can do. But in the parallel wrap that we will use in the future, it will complain. So if possible, try to keep it with integers, numbers of this one, so multiplies of this one. And if you have a specific value like 3.46, because you have an instrument that is giving you that precision, then just try to compute n times that number here and here. So, but just try to keep it as exact as possible, because otherwise in the parallel wrap, it will complain. Okay, so I think we have the first file. Very quick summary. So this is the line index, and this is the spectral range, and this is the spectral sampling that you want to have. Okay, so now if we go back to the control file, you will see that the next one is the line list. So then let's go to the line list. And here you have a lot of information. I think in the manual is explained, but I will try to briefly summarize what you have here. And also I will try to show you later as an exercise how to create one entrance in this line list. So how to create all these input parameters. So if you have a new line that you want to use for your work, how to do it. Okay, so in the first one is the index. This depends on you, so you can change this number, so you can move this line to this part. I put it as organized as possible, so it's increasing wavelength, but the idea is that you can always put it somewhere, so the code will not complain if the wavelength... Sorry? Okay, I think it was not for me. Then you have to put the element. It's usually in capital letters and the first two ones. Okay, and then this is the ionization stage. So usually, so in this case, all are neutrals. Then wavelength is in Armstrong. Then this is a value that was mainly used in the past, and is for adding an additional enhancement of the line. But in general, if you put 1, it's using the Unsol approximation for computing the broadening of the line. But these days we use the broadening due to collisions with hydrogen that I briefly explained last week. So if you have these two parameters here, then the code will jump anything that you put here. We are keeping it because if someone has an older file, you can run it without errors. But the idea is that this value is not used anymore if you provide these ones that are more accurate at the end. Okay, so then you have the excitation potential. That is essentially the energy of the lower level. I will enter in details later, so don't worry. This is the product of the log GF and the atomic configuration of the lower level. So this is 2s, so the spin, so 2s plus 1. And this is the angular momentum. And this is the total angular momentum, J. And this is the same for the upper level. And these are the two broadening coefficients that I will cover this in the future. So essentially, you have an information here. I provided a lot of spectral lines, so probably with this you can start. And later on, I will explain you how to create one of these files. But the important thing is that imagine that you said, well, I like, for example, 6173 because it's the line that, for example, HMI is observing, or is the line solar orbiter phi is observing. So then you have this index 5. So then you go to the wave grid and you said, I want to add a new line in this computation, and you just put here 5, and just as a initial guess, you can put it like this. So minus 500 with a step of 10, and then 500. So for example, if you run the code, it will complain. So if you do this, so now you have 3 lines, okay? And this line is the new one that we added, and these are the previous 2 ones, okay? So let me remove this. And then we run it and we have it here. Okay, so let me go a bit more with the other files, and then I will check if you have any questions, or if not, we can move to the second step. So then here, the third file that we need to provide is the abundance file. If you open it, it's using one of the conventions for defining abundances. You have that index here are elements, and this is the abundance. So you can check. In principle, we are following, I think it's 2009, so Asplund et al. 2009. But as I said the other day, if you feel that some elements, they have an abundance that you believe is not correct, or you prefer to use another one, then you just need to change the code here, and you are fine. Okay. So then what else is, sorry, it's missing. Yes, the next one is the atmosphere. I have here one example. Again, I think the description of each column and each value is presented on the manual, but if not, just let me know. I will just briefly describe you what we have. So we have 3 values. And so the first one is the macro turbulence correction. And the idea is that this represents, so when you have a given spectral resolution, this can be represented as a point spread function. And in this case, if you put a number here, you are given the width, and the full width half maximum of that point spread function. So then the code will convolve the profile that you are synthesizing with that value. So then it's a value that it will not depend with the atmosphere with height. So for this reason, it's just one value here. The rest are different parameters that will change with height. The same with the second one. This is the filling factor. And what we are saying here is that we are doing a synthesis with an atmosphere that is occupying 100% of your element. But the idea is that when you do inversions, if you feel that your spatial resolution is limited or something else, then you can change these values. But again, it will be a factor that will play with 2 atmospheres. So it's not something that will change with height. It will be just a percentage. So it's a single value. And then also the third one, that is straight light. So you will have the possibility of giving the code a straight light profile that it will represent some contamination that you could have in an instrument. And this is the weight of that straight light on your observation. So it's also something that will not depend on height. So, and then we start a series of 11 columns, and each column now it will change with height. They are physical parameters. Just as a reference, you can check it later with the video, with the manual, but this is optical depth. This is temperature. This is electron pressure. This is microturbulence. This is magnetic field, velocity, inclination, azimuth, geometrical height in kilometers. There was an error on the manual, but I changed it and I will send you the new version, but this goes in kilometers. And this is gas pressure and this is gas density. Okay, just as a note, the initial version of Hsra, it stopped here. It only had 8 columns, I think. These 3 new columns, they were added at some point. And the idea is that when you are doing inversions, you are basically just using the first ones that I mentioned until azimuth. Geometrical height, gas pressure, and gas density, they are computed after the inversion, assuming hydrostatical equilibrium, and they are based on combination of the other parameters. But the code doesn't use those atmospheric parameters for anything during an inversion. Okay. However, when you are doing synthesis, when you are doing the transformation of the atmosphere, as I will show you later, so if you have an atmosphere from a simulation and you have the geometrical height and the gas pressure relation, then the code will read those parameters and will compute the relation of temperature and electron pressure based on those parameters. But essentially, for inversions, those 3 columns are computed after doing the process. They will not participate in the process. Basilio, is that right, correct?
Nearly. It's not needed a hydrostatic equilibrium. Is you specify hydrostatic equilibrium, but in other case, just transform temperature and electronic pressure to gas pressure, density, and height.
Yes.
Hydrostatic equilibrium only is you say that.
Yes, that's true. So depending on how you configure the code, it will compute in one way or the other these 3 columns. But the message that I wanted to emphasize that they will not be used during the inversion process. It will be always the relation between optical depth, temperature, electron pressure, and then the rest of parameters that you have here. Okay, so let me go to the next step, and here this will be mainly used in inversion, so I will explain it later. So basically, I think the rest of the profile, you probably don't need to focus too much on them now, on it now. So just let's keep these files as a reference for today, and then let's go back to the example. So as I said, I'm calling this control file, I'm asking Hsra to run it, and then it's providing a result that I'm reading with this ideal routine. I think Basilio probably has another one. And the idea is that I'm reading this file. So you can see this profiles.pare is the file that I define here as upset profiles. So the output of the synthesis is what I'm reading. And I'm saying, tell me the index, the wavelength, and then Stokes I, Q, U, and B. Okay, so then you can do a plot. Maybe just move it a bit up because maybe it's in the bottom. So plot SI, you will have it like this. Well, let's plot a lamp. So this is with the wavelength vector, okay? But remember that we are always working on polarimetry. So we have the full Stokes vector. So you can plot one of the linear polarization states. So this is Stokes Q. And then you have Stokes U, okay? And then you have Stokes B, okay? They are always normalized to the continuum intensity. Okay, that's a question. Yeah, Dato, yes?
Carlos, I noticed that in your Hsra atmosphere, the magnetic field input was 0. So how the code still synthesized the non-zero Stokes V?
Yes, sorry, I didn't want to confuse. So the idea is that in the troll file, I'm calling this atmosphere.
Oh, okay.
But this was just a reference example. Okay, so this is a Hsra, but the one I'm calling is that one. So if I go to the folder and I open that one, it has different values.
I see, thank you.
Okay, yeah, I thought how I do it, because the idea is that later in the next example is how to create an atmosphere and given values. So I thought if I keep it open, I will start overwriting it. So then by the time I'm giving the class, you will see an atmosphere that is changing continuously. So I said, I will just use as a reference for explaining the columns in the Hsra, but the one I'm using, it's in fact some different one. Okay, so I will
have,
yes.
Sorry, it's Svetlana. I have a question. You said that you don't use gas pressure as a parameter, but you need this for computing continuum opacities. How do you calculate continuum opacities then?
Basilio.
Yeah, okay.
Yes.
We are not using gas pressure as an input parameter. You are using temperature and electronic pressure. Yes. And internally, we evaluate gas pressure. The idea is that if you like to synthesize a profile, you only need to give two thermodynamical parameters. You can choose temperature, gas pressure, and so on. We are giving temperature and electronic pressure, and internally the code is evaluating gas pressure. Okay. And then for the inversion is the same. We need to only allow as a free parameter the electronic pressure, and as a derivative magnitude is the gas pressure evaluated. Okay.
I see. Okay, thanks.
Okay. So yeah, so going back, the atmosphere that we're using for the synthesis, it's this one. Okay, so this one has magnetic field. So for this reason, we can see the Stokes profile. Sorry, I think maybe I confused you, but just keep that in mind. So we are now in the next step. We are going to create one atmosphere. So then just let me go back to where I was. The idea is they are normalized to the continuum. So Stokes I it's normalized to the local continuum. So you always have that your continuum is going to be in 1. And then your Stokes parameters are normalized to that. So in this case, for example, if you want to have in percentage, you just multiply this by 100. So sometimes in observations, they said the Stokes V signals are, for example, 10% or 15% of the continuum intensity. So then what they are giving you is this Stokes V multiplied by 100. I think there's another question. Yes, Anjali?
Carlos, so you talk about normalization values. Does it matter to Sir whether you are normalizing with respect to the local continuum or the global continuum?
So can you repeat the question? Sorry.
Does it matter if you're normalizing a profile to the local continuum or the global continuum? I mean, when you have...
You're right. It's not normalized to the local continuum. It's normalized to the quiet sun continuum, to the Hsra continuum, in fact. Then it's not
yes,
one. It's one if your atmosphere is like a quiet sun mean model, average model. If not, you will have other value there. Okay.
But Basilio, but let me confirm. I think we are normalizing to the local continuum, right? Because the continuum is increasing. If it's changing with wavelengths. But every time that you do a synthesis, the local continuum is 1. Right?
Local in the sense of wavelength, but
yes.
not in the sense of the atmosphere.
No.
Okay.
Yeah, maybe I was confused. Yes.
The idea that's a bit confusing. That it's local with wavelength, but so for each line, the individual wavelength.
Yes.
Exactly.
Yes.
But it's it's not always 1, because if your atmosphere is hotter or cold or cooler, then you will have a different value there, because this is normalized to the average quiet sun model at this wavelength. Okay.
Yes. So let me try to explain again. So if you put here another line.
Another clarification I need.
Yes, 1 second. Yes, 1 second. So if you synthesize 2 lines like this, and then you do like this, you can see the continuum is 1, but this line forms in 50 to 50 Armstrong, and these 2 forms in 601. So the idea is that we are not seeing the evolution of the continuum when you change wavelength. So every time that you do a synthesis of a given spectral range, the continuum is 1. So this is in the case of this atmosphere. So if you have a cool atmosphere, it will drop. But the idea is that the continuum will be the same between the lines. So if you use a cool model and the continuum in this region is 0.8, it will be also 0.8 in this line. This is what I meant. So I meant that every time that you have a spectral range, the continuum value will be the same between different lines. Okay?
But do you provide this? Do you provide the value of the continuum flux to revert this? Because if you want to have it to locally in space also normalized to the cool atmosphere, do you provide that value?
Not in fact, you when you have observation, you will take the quiet sun zone, and then you average that and you normalize to this value. Then you will normalize to the average continuum in the center of the disk and at this center. Okay. If not, you will need to calibrate with the center to limb variation. Okay, then the idea is,
that's clear. Yeah. Well, these are observations, but in theory, you have a value of the continuum flux or intensity.
Yeah. This is internal in the code. We have.
Is it printed anywhere in the file that you can look it up?
There is a there is a, I don't know, continuum Hsra procedure, and also there is some files in some places in which there is a table with these values. Yeah.
Okay.
I think Anjali, you have another question.
No, Basilio's explanation clarified it. Thanks.
Okay. So then, where I was, yeah. So I think. Yes, so I just was saying that you have always the 4 Stokes profile, so please take a look at them. And just, I put here an exercise, just if you want to check. And the idea is that when you synthesize with this grid file, you will have a wavelength range that, as I said, it goes respect to the center of the line. So if you want to do a plot where you instead of, so if you do this, so just as an exercise, try to put this in the absolute value, because now it's referred to this line. So the only thing that you need to do to check that value is to go back to the lines and then pick this wavelength, and then this will be your 0. Okay, so then you can make the plot. Instead of having this in milliarmstrong, you can put armstrong. Okay, if you cannot do it, just let me know through Discord or something like that. But it's just to see that there's a strong connection between the grid file and the line list. Okay, so the next step is, I think, or I hope that more or less you followed the explanation. So then what I'm going to do now is, we had one atmosphere. I don't remember which one was, but now we are going to create one. So I'm going to read this model, that is the Hsra model. And with this procedure, I think it's the same of Basilio's one, or maybe a bit different, but just you put here elements, and the idea is that it's reading optical depth, temperature, electron pressure, microturbulence, field strength, line of sight velocity, inclination, azimuth, microturbulent velocity, filling factor, straight light, and then geometrical height, gas pressure, and density. So with this procedure, you read all those values from the previous atmosphere, from this one, okay? And then you can add values. In this case, I said, let's try first with a constant stratification with height. So I'm putting a magnetic field of 450 Gauss. I'm adding velocity. It goes in CGS, so it's centimeters per second. So I'm adding here 1 kilometer per second. Positive, so it means time flow. And then I'm including 30 degrees in inclination and 70 degrees in azimuth. And I'm not using any microturbulence. Okay, so in this case, I put a stop. I run again the script, and you will see this. And I think it's the same case as before. So just let's put here 2000 Gauss. And then you see that the profile has changed, okay? And this is an effect of the Zeeman splitting due to the magnetic field. So here, I just wanted to show you how you can read a reference atmosphere and then how you can add values. You can also add temperature and make it cooler, make it hotter. And so the idea is here is just you take one, you add new values, you write it, and this is the name that you have here. Okay. So if you change this name, then you have to update it here. And then you just run the code again. So the only step that I added here is to read an atmosphere, change some values, and then write it, and then call again the code, read the profiles, and then plot them. Okay.
I have a question here.
Yes.
Here. So when you said that you can change temperature the same way, that would be like a shift, and you put gradient, different gradients there, like whatever you want.
Yes. So yeah.
Yes, and that's clear. And what do you do with electronic pressure then?
Is computed based on the change of temperature, right?
Is there a code to compute that?
No, I think if you change it, well, Basilio, maybe.
If you do not run any program, then you are keeping the electronic pressure just constant. In the example of Carlos,
yes.
He's reading a temperature and electronic pressure, and he is not modifying. Then
yes.
if you like electronic pressure compatible with this temperature, we need to run other program that is called Modelador.
Yes.
It evaluates the electronic pressure compatible with temperature under the hydrostatic equilibrium hypothesis. So you can.
Okay. Yeah. So there is a recipe. That's what
yes. You will need to change that.
Okay. Good.
Yes. Yes. The idea is that I will send today or tomorrow all these files and also a library with atmospheres, and they are from publications. And then there you have representative model of umbra, penumbra, white sand, and there all the parameters are consistent. So the temperature in the umbra is much lower, but the electron pressure is related with that temperature, and also magnetic field and other parameters. But in this case, it's just that, just for quick check, you can change things, but yeah, it's the electron pressure is not updated based on the temperature changes. Okay, so then just because I went too fast, so just to show you, so the idea is that with the original temperature, the continuum was in 1, and then if you change the temperature and you make it cooler, then the continuum just drops. Okay, so then my recommendation here, mainly for the young people, is to play with different values. If you increase the temperature, what happens to the profile? If you increase the magnetic field, or you put a magnetic field is 0, what happens with the profiles, and so on. So just try to play with different combinations and try to get use of how the profiles could change based on a given atmosphere. Yes. And then I think the next step is, yes, is to add, is the same example as before, but in this case, I will add a line of sight gradient. In this case, I'm adding a velocity. Just let me run it. So if you do plot tau, that is optical depth, and bell, you divide it by 1.5. So this is in kilometers. So I'm putting a velocity that is linearly decreasing with height. So it means that the line of sight of velocity is changing. So you have gradients along the line of sight. And in this case, if you run it, you will see that now the profile, they don't look symmetric. So they do have extended wing in this right side and in the other right side. And this is because you have a gradient. So also this is an exercise to just give you an idea that when you have certain shapes on the Stokes profiles, let me show you Stokes B. So when you have these type of shapes, before it was a uniform shape, and now you have one side that is much larger than the other. So when you have this type of shapes, you have already some intuition that there are some gradients along the line of sight, probably velocity, probably magnetic field, probably both. So it's just to give you an idea that if you see this profile, then you cannot try to embed them using constant, for example, magnetic field or velocity. So you need gradients. Okay. And I think this is the first part. So I will send you this procedure. Just let me make this. Just 1 second, so you can see. In this case, like this. So I will send you this procedure. I recommend you to go first step 1, try to understand what I said. Then first step 2, so you can play a bit with atmospheres. Then step 3, it's an additional step with playing with atmospheres. And then step 4 is just try anything that you can think of, because I think the code will work most of the time, but sometimes it could be not realistic, the solution. So it's good that you just play a bit and try to build some intuition for later. Okay, so I think this is the first block that I want to cover today. So is there any additional question that you would like to ask before moving to the next one? Okay. Okay, so then the next one is, let's try together to create these two lines. Except these last two values, we will try to look for how to make this entrance here. So you can, in the future, if you have a new line in your observation, you will be able to create this file. Okay. So then the first thing I usually do, and of course there are several ways of doing this. So if you have a different one, it's fine. I hope it's we have the same results. But the idea is that I will explain you how I do it, and I think it's okay. So the first thing I do is I look for the atlas. In my case, I go to this web page. So if you type BAS 2000 solar spectrum, you will go to this web page, and then you will go to solar spectrum, and it will be here in general. So yes, okay. I think there's something. Oh, okay, there's a chat. Oh, I was not reading the chat. Okay, I think I think Ivana likes the web page. Yes. So the idea is you should know the wavelength range that you observe. So in this case, let's go to 6,300, and let's put 10 Armstrong. So if you see probably the VISP calculator, you will see that they are predicting that this wavelength range will be observed. I think in cycle 1, it's already included. So you will have something like this, okay? So imagine that you don't know what you are looking for. So this web page, sometimes if you click here, they give you some information, and sometimes it says it cannot found, but at least you can try to click. In this case, it was no result, but at least you can move your cursor, and then you can see more or less where the line core intensity of the line is. Before going further, you see that there is one broad line, there's a two, and this one is very thin, this is very broad, and this is very thin. In general, people know more or less what type of lines you can have. But if you see a very, very narrow line, then, and you are observing from the ground, you should assume that they are from the Earth's atmosphere. So this is not related with the sun, it's just absorption by the Earth or atmosphere. And one quick check is that if you have a map, just pick different pixels, for example, in a network or in Sunspot, and you will see that these lines are changing a lot, but these ones are always the same. So then it means that they are from the Earth's atmosphere. Okay, so in this case, we are going to focus on these two lines. So let's make it bigger. Okay, this line and this line are our lines of interest. Okay, so the first thing I do, so let's check here, it's a 6301.5. So the first thing I do is I go to the NIST webpage. So again, here is the same, you type NIST, line list, and something will appear, and then you go there, okay? So let's close it. And then you are on lines, and then we said, imagine that you don't know anything at all. So you said, okay, I know that there's some line, oh, sorry, what's this one? I know that there's some line here, but I don't know even if it's iron, silicon, or carbon. But you know more or less that the wavelength is 6301.5. So then you put here 6301.4, for example, and then 6301.6. This is in Armstrong. And then we are interested, you click here in show advanced settings, and then you go down and you ask for the product of the GF, so the log GF factor. And then you click in retrieve data. And then you have that there's one line in 60150, that is the wavelength of interest. And then there's something in 41, but if you go back, sorry, let me close this one. Oh, zoom is in the middle. Sorry. The zoom options are in the middle, so I cannot, yeah, sorry. So you go here, and then you said, I'm interested in 5. I think in 4, there's probably no line. So then sometimes you have 2 entrances, but if you don't have any information here or even here, then it's probably not so important. So then you can assume that in this case, the line that you have is this one. So it's an iron line 631.5. Okay, so let's go back. In this case, we know which lines are, so you can write iron 1 here, and then just put the full spectrum. So now we have the two lines that we are interested on. Okay, so then the first one is wavelength. So if you have this, and I hoped I will try to go slow, so you go back, and this is, so first you have that this iron one, okay? So you have it from before, and this is the wavelength, okay? Sometimes it's not exact, sometimes it changes a bit depending on the user, but I think it's safe to assume that this is correct and similar to this one. Then we said that this will not change in general because we are going to provide more accurate parameters. So then the next value that you need to compute is this one. So then for this one, I said is what in a manual, I think is called excitation potential, but it's essentially the energy of the lower level. So this is the energy of the lower level, but as you can see, this is in centimeter minus 1, so you have almost 30,000, and it doesn't look like this 3.6. This is because it's in electron volts here. So then you just go here, you copy this value, and then you type electron volt to centimeters minus 1 or the other. I usually use this one, but you can choose other tables. And then I just copy the value here in centimeter minus 1. You see that there's an error, but because in the NIST database, they usually include a space here, but now it's done. And then it says 3.6536. And if you go back, is 3.654. So sometimes there are some, yeah, it's correct. So it's this one. Okay, so then you have another value that is the excitation potential. So then the next one, this I said is log GF. Okay, so then we go back and usually needs provided. So if you go here, then this minus 0.718, it's here. Okay, so it's the same value. You can copy it here. Then I said that you need a spectroscopic. Yeah, Alberto?
Yes, Carlos, you can get the energy in EV from the web page, from the NIST.
Okay, that's good to know.
if you go back in your NIST
to advancing.
Yes, in output options in energy level units, you see centimeters minus 1 in the
here
left hand, no left. Left panel,
okay.
There.
Okay, good. As I said, we are all learning.
And then you can click retrieve, and you will get these values.
Okay, good to know. Thank you.
Yeah, very well.
Okay, so then you don't need to do all the things. Thank you very much. Okay, so then the spectroscopic notation. So as you see here, it says 5p20, and the idea is that you have it here. So this is, you don't usually use this one for SER, or for the computation of the broadening with hydrogen, we will use it later, but essentially you use only this last part. So this is 5p2, and you just copy 5p20 with a space in between. And then the next level, you just go and set, oh, sorry. It's not complete here. And then you have this 5D2 that is, yes, here, 5D2. Okay, so again, very quickly, the ion, so the atomic element, you have it from before, then wavelength, then the excitation potential. Now it's easier than before. Then the log GF, spectroscopic notation, and this we will cover later because it's the same for this side. So I decided that this is a bit detailed. So I thought we can do it later. And the only thing is that I chose this example on purpose because, as you can see, if you try to do it for the second line, you will have the wavelength, yes, then this is the same here, but then there's no log GF value. And this sometimes happens. So there's different databases, but in my case, what I do is to go to the Courage database. So in this case, it's similar as before. So if you try Courage line list, you will get to this web page. There's a detailed explanation here of what you have in each file. But what I usually do is I go to this GF100 because it's in 100 nanometer intervals. And then I look for the line of interest there. So they are structured that this value is the last one of the range. So as we are looking for 6301, we have to start with this one, okay? And there's a lot of lines, so you just move down, 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 down. 1 second, will take some time. Okay, okay, so we are looking for 6302.5, okay? So more or less around here, okay? So then this is the log GF, and this is the atom, the element. So as we found in NIST, these two are iron, so we need to look for 26. Okay, so in 602.5, 2.5, what I'm missing here? Sorry.
Higher up.
Yeah,
Carlos.
this one. Sorry.
So, no.
7, no? Iron was the mark.
This one, sorry.
It's the third line.
This one, sorry. So,
yes.
So, but the idea is that you can see that sometimes they are very close, and you see that it's 26 and 2601. So what I do is just check that energies and the levels are the ones that I'm looking for. So in this case, you see that this energy is in fact larger than this one. And this is because the database, it will change the energy levels based on parity, not based on increasing energy. So sometimes the level with higher energy is the first one. Sometimes the level with lower energy is the first one. But the idea is that you have this energy that now we can, okay, let's go back. So we have it here now in centimeters, and then retrieve data. And then you see that it's 29,469, and you have here 29,000 something. So it's this energy, and then this level is 5p or 1. That I think is this one, if I'm correct. 5p 2. What I'm doing? 5p. I'm confused. Is this one right? Yes, this one. Yeah, is this? Yeah, is correct, right?
Yeah, but they're because the energy levels are interchanged. Also, the labels are interchanged. So
yes,
that's why you look at the second label.
Yes, yes. So then, when you know that you have the proper transition, then you can have a log GF value.
So Carlos, one more thing about the third column, the element.
Yes.
The dot 01, the dot 00 and the dot 01 are the ionization. Yes.
Yes. Yes. Yes. So then these 1 or 2 are the ionization levels. So this is iron 2.
Yeah, iron 2. Yes.
Yes. Yes.
Sorry.
So then I have here 1.131, and then if we go back, this is the value I chose for this second line. So if you don't have it in NIST, I usually go to the Kurux database and I try to get it there. They are sometimes not the best ones, but at least you can start from there. And if you want to improve them, there are some options to do it. But at least is that you are consistent. So you go either to one database or to other database, or other databases that you can use more frequently. But the idea is that I use Kurux because I also use it for RH, and for me it was easy to more or less move around. So later on we will use this list for RH. I think there's a chat. Oh, let me see if chat.
Yeah, it's just for me.
Okay.
I'm leaving. I have to leave now.
Okay,
Thank you so
okay.
much. I will
Yes,
join next
yes.
time.
Thank you, Svetlana.
Bye-bye.
Bye. So then I think this is more or less what I wanted to tell you today. Let me just briefly summarize. So this, you can basically create it with NIST information, but sometimes there are some missing elements, and I usually go to Kurux. And the idea is that I go there because also for RH, you use it. And for me, it was comfortable to do it. But there are also some databases like Valdi or other databases. So the important thing is that you should know what you need to put in each case. And what I wanted to show you today is how I do it. But in principle, you can always choose a different option. The important thing is to know units and what is in each case. Okay, so I don't know if there's a question. I think someone in the chat said something, but yes, 1 second. Okay, so how important is to have the electronic configuration correct? Ryan, so what do you mean by electronic configuration? You mean this 5P10?
Yeah, that.
Ryan?
Can you hear me?
Yeah, now I can hear you. So
yeah, so how important is it to have that configuration written correctly? Because I have changed it just as an experiment and it made no difference. So I was wondering if it's actually used.
No, I think it's crucial. I think you have, maybe Vasily or can correct me, but I think you need to really have this correctly.
If you are referring to quantum numbers, to the multiplicity, and so on, G, etc., it is needed for Q, U, and V for
yes,
a Stokes profile.
For
but for
Zeeman.
intensity, is not for intensity. You don't see any. If you change this electronic configuration, you don't see anything changing in the intensity profile. You will see that it's changing the size and the shape of the Stokes profiles. Okay,
yes,
but Q, U, and V.
Yes, so they will define the Zeeman pattern. If
Yeah.
we can say it in another way. So
yeah, but related to that, maybe Ryan was talking about the letters that denote terms. Maybe he had J numbers correctly, and then I also would suspect that these 5P, 5D are not used.
Yes, exactly.
Correct me if I'm wrong.
No, but they are used to evaluate the splitting Zeeman. The Zeeman splitting is evaluated in terms of that. The you can play Carlos if you like. If you change this value, you will, for instance, you change G or the I don't know.
So
the shape of the splitting Zeeman will change. No Stokes I, but Stokes Q and V will change because depends the number of components of the
yes,
Zeeman.
I think that the Zeeman pattern is defined by L, S, and J.
Yeah, you need to have L from the letter and S from the first number.
Yes. 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 Maybe Ryan, if you find that example with the Stokes profiles, then just let us know, because for me, I think you need them for finding the Zeeman pattern. But I think there's another question in the chat. So if you have a question, don't worry, just raise your hand and speak, because it's okay. That is true. Okay, Ivan. Okay. Okay. So you are seeing the chat when I show it in the screen, or not?
Yes.
Okay. Okay. Good.
There is other programs like there is one program that's called Lande that it is with the library, and if you run Lande, it reads the files in the lines, the atomic file parameter, and evaluating all the Zeeman components, and then you can check how it's changing the Zeeman components when you are changing the quantum numbers, the electronic configuration.
Okay. Okay, thanks, Basilio. Okay, I see 3 hands, so let's start with Dato. Yeah.
Carlos,
yes.
So does SIR inversion or synthesis requires the damping parameters like damping sigma and damping alpha?
You mean these two?
Oh, last two is damping parameters. Oh, okay.
Yes, so this is, I think, sigma and alpha, if I'm correct, if not alpha and sigma, but they are not required. So if you have them, then they will be used. But if you stop your file here, it will use unsold and it will read this value. But if you have them here, it will use them as a default and it will jump this value. Okay.
Okay.
So in general, all the files that we will give you, both for SER and for design, we will try to always give them to you with these 2 damping parameters. So the collisional, so the broadening due to collision with hydrogen. Okay. That is the best or the most accurate approach we have right now for including that broadening.
I see.
Okay. Okay, so I think, Alberto, this hand is from before or you have a question?
That was for before.
Okay, thank you. So then, Anjali, you have a question?
Yeah, it's regarding Svetlana's question.
Yes.
So when you are introducing a temperature gradient in a new defined atmosphere, you mentioned that the electronic temperatures are not automatically modified. And if you don't do that...
No. So one second. So in this case, I'm changing the atmosphere by hand and running the code later. And then in this case, it's not compatible because I'm not changing anything. But internally, when you're doing inversion, when you change the temperature, the electron pressure is also updated.
Oh, it's simultaneously modified by the code.
Yes.
Okay.
Yeah, it's just in this case because I was modifying a file like this one. So then I was just changing the temperature. So then the electron pressure was not changing because I was not doing it. But internally, the code, when it's running, doing an inversion, it will perturb the atmosphere. And if you change the temperature, then it will recompute the electron pressure compatible with that temperature. And then it will go from there.
Okay.
So it's consistent. It's just that in this case, maybe it was my mistake how I did it. But it's just that if you are playing with these values or you change this column, the other columns are not updated because I'm just changing this script. But the code internally is doing things consistently. Okay.
So even if you only change this model's individual parameters, the code will take care of all the rest of the parameters.
The relation between temperature and maybe Basilio can add something, but the relation between temperature and electron pressure will be kept if you don't invert, well, it will be kept, and the other parameters like velocity and magnetic field, it will be based on your configuration. So if you said, I want to invert a profile, but I don't want to change the velocity, then the code will use the velocity that you give. But every time that it changes the temperature, the electron pressure will be updated based on that change.
Oh, okay. That's all I wanted to know. Thank you.
Yes.
Exactly. If you are running in a synthesis mode, you are reading this model, and if you change one parameter, the other are keep constant. You are not, but during inversion, you present an initial model, and when you are changing some parameters, you can say how the other parameters can be modified. If, for instance, in the case of electronic pressure, you can say the program to say, okay, if you put 0, the program understands that you are in hydrostatic equilibrium, and then any change in temperature will produce a change in the electronic pressure following hydrostatic equilibrium. But if you put, for instance, as a free parameter, 2 nodes in temperature and 2 nodes in pressure, both are free parameters, and then it's not hydrostatic equilibrium imposing. Then just any change in temperature depends on the nodes, and any change in electronic pressure also in the nodes that you are allowing to be free. But I think that Carlos is explaining that later.
Okay.
Yes. I think that's a question from Alberto.
Sorry, which one?
You have your rise. You raise your
No,
hand, right?
that is still the same as before.
Okay.
I have not.
Okay. Do you
No
want
problem.
Okay. Do you want that I can remove your, maybe? No. Can you?
I
Well, it's
don't
fine.
know.
It's fine.
Okay.
I think you can click remove my hand, but it's fine. Then I will understand that it's there. Okay. So then I think at this point it's more or less clear what I said today. So can I move to the next step? Okay. I think yes. So then this is what I had. So homework. It's very simple. So it's just try to run a synthesis. I will send you the files later. So just try to check if you obtain a profile and if you can read it and how does it look. Then I think I recommend you to play because it's one way of learning things. But for me, the most important thing for the next class is that you can try to create an atmosphere that more or less is similar to the one you have. So for example, if you are interested in Umbra, we will send you the atmospheric models that represent Umbra. But just to give you an idea, so you will need an atmosphere that is cool, and also the field strength is large, the velocity is almost zero, and more or less you can have an idea. So if you are interested on quiet sun, maybe you can play with atmospheres that has a weak magnetic field. If you are interested on, I don't know, penumbra, so then you can play with atmosphere that has a magnetic field that is inclined and has a certain strength. So I guess that you can play a bit with scenarios that you want to work on in the future. Because the idea is that then we synthesize with that atmosphere, then we can perturb the profile in any way. So for example, adding noise, and then we can run the inversion of that profile, starting from a reference atmosphere, and we will check how the code handles to fit that profile. Okay, so
maybe later you will explain how to modify electronic pressure if you are changing temperature and you want a consistent model, for instance, using modelador 3.
Yes, but I think for this exercise, and maybe I'm wrong, so you can correct me, but I think the exercise is you change an atmosphere, you run a synthesis, and then you try to get to that atmosphere. No, yeah. If you try to get to that atmosphere, maybe the electron pressure is not correct. But yes, sorry, yes, you're right. But just take the atmospheres that we will send you. You have there Umbra models, you have penumbra models, you have quiet sun, and just play a bit. And the idea is that later, mainly if you change magnetic field or velocity, you can try complex stratifications, and then we will try if the code is able to reach them. Okay, so just create models that you would like to fit with the code. So then to get familiar how to use it and how to define nodes and things like that. Okay. Yes, this is what I was saying. Keep the atmosphere. So then we will compare with the one the code obtained, and we will check if it's similar to the one you had for the synthesis. And then I recommend you to try to repeat what I did. So to say, okay, imagine that I don't know what are the two lines in my spectrum, this iron pair. So can I go to the NIST, check, and then find the information, and then fill all the columns on the line list? I think this is a good exercise. And as I said very early in the beginning, the same input file will be used in Desire. So everything that you can learn from this part, from Hsra, you will use it also for Desire. So it's very useful. And then, yes, I'm repeating. Okay, and this, I put it as an extra. Just let me show you very quickly, because I will send you also the file. So where am I? Yes. So I will send you this folder that is called Synth1, and I will also send you this Atlas file. So here, what I'm doing, if you run it, it will do the same. So it will run a synthesis. It will read the profile. but also it will read one file that is called Atlas 630 nanometers txt. And what I did was I went to the, I went to bus. So imagine that you have this. So then you click here in this icon and you will have the wavelength and intensity. So you can download the Atlas, okay? And when you have the Atlas, you can run the synthesis using a reference atmosphere like Hsra or FAL. And then in this case, if this works, okay, let me see where I start. I think here. I think it's a bit big. Yes, let me make it smaller. Okay, so in this example, the white line is the Atlas. You can see that we have these two telluric lines. And the red one is the synthesis, in this case using FAL. You can try with Hsra or FAL-C. I think FAL-C seems a bit better for trying to reproduce the Atlas, but I think you can try different models. But the idea is, if your atomic parameters are reasonable, then you will have something like this. So here is just a comparison, a synthesis with SER in red and the Atlas in white. And you can see that they are very similar. So this line depth and here is very close. If for any reason, the profile that you obtain, it's much, much lower here, or much, much higher intensity, then probably there's something wrong in your atomic information. So just check that. And I will send you the file, so you will have this one. So you will see that it's here, so you can copy mine, but you can also try to download it yourself. And the only thing that I put it here as a note is that the Atlas that you have here, you can see that it goes up to 10,000 K. So it's not normalized. Well, it's normalized to 10,000. And as I said, SER is giving you the profile normalized to 1. So I did it just for a simple comparison. I normalized the Atlas to the first value of this wavelength range. And I'm normalizing also the synthetic profile to the first value of the range. So for this reason, for this reason, you can see that they both match in this point. And then the rest, they are very similar. And also just keep that in mind that for comparing with the Atlas, you need to change one vector, or to change the Atlas to the reference wavelength, or to just add the computation of the line, and then they are both in the same wavelength grid. So just give it a try, and it's a good way of checking if the new lines that you're adding, they have a proper atomic configuration. If there's a mistake there, you will see it very quickly when comparing to the Atlas using in this case is a FAL-C model. Using this model, if they are not close, then something is wrong in your atomic configuration. Okay, so then I was here day 2, and yes, so sorry, I covered this. Just try it as an extra to compare with the Atlas. If you try a new line, it's also fine. You can follow the same steps. And then for the next class, I will start with response functions. We will learn how to run it for a given atmosphere. We will try to read it and to try to understand what they are. From there, I think we will get a feeling of how to do inversions and what type of atmospheres you can use, because you will see that the spectral lines are not sensitive everywhere. So maybe this will give you an idea of which atmospheres you can use. And then I think we can probably prepare inversions. I think it will be a bit more explanation, but probably you are more or less comfortable with the code by that time. So probably we will run inversions. And then after that, and I think this will be the next class, we will learn how to use the routine Basilio was saying that will evaluate a given atmosphere and compute other atmospheric parameters consistent to that atmosphere In one case could be updating electron pressure. In other case could be computing from geometrical height and gas pressure, an atmosphere in optical depth and temperature. So we will learn how to do those things. And basically this will be the Hsra part in the single node. Then we will jump to the parallel version and we will do probably more cool stuff. Okay, this is a question. I don't know. So I think next week is Easter. That I know. But I think Friday is probably not a day that we will have class, right? Maybe someone.
It's a holiday here in for us. Yes.
Yes. So for me, I think it would be okay if we want to move for next week the class to Wednesday, and if you want to have the class on Wednesday, is fine. If you want to give it next week, so next Friday into Fridays, for me it's also fine. So I think you can decide, but for me both options are okay. So next Wednesday or Friday in 2 weeks. I think I'll
Yes, this is a new.
This is a new hand. Okay. Okay.
I learned how to put down the order. Sorry.
Okay.
No,
okay.
just a comment because there are a couple of routines where you can read the solar atlas in IDL, and you don't need to go to the web page. That I like it very much, but in IDL you can get these. They are called FTS read.pro.
Mm-hmm.
And the other one is called Red Atlas, and it's in BISP. It was written by Roberto for BISP, so you can find probably. But FTS Red.pro has been there for many years, and it's sold as the optical spectrum, so you can get the for calibration and these things.
I think that's great, but I wanted to show BAS 2000 because for FTS Red you need to install the atlas in.
Yes, I really like BAS 2000. Sorry, yes. But
yes.
but sometimes when you are coding and you want to look calibration and this thing is nice. Yes, you have to download the data file, of course.
Yes. Yes, and also I hope that some people will make these programs in Python. So probably
there is a version in Python that Jaime has available. So I have used that also in Python.
Okay, that's good. Thank you. Okay, so then Ivan, do you wanted to say something or?
I had some question for after we are done. So if you're gonna stay here a little bit, no.
Yes.
I just wanted to vote, but of course it shouldn't matter to me. I would vote for the Friday in 2 weeks because there are also a lot of other things happening. So maybe every week is unrealistic to begin with. Okay.
We have our oversight committee meeting in those days as well. So.
Okay. So then let's leave it for. Into Fridays. I will send the link with information, and then you will have more time, maybe if you're on holidays now, but maybe you will have some time for trying to revise everything that I said, that I tried to go slow, but maybe I went a bit fast. So just maybe it's better for you. So then I think this is the end of today. So I will stop sharing. And if you have questions and you want me that I share again, it's fine. And I think we can have like 10 or 15 minutes of questions related with what I said today. And then my advice is that you should try it by yourself. And then next week, if I see that there are some thread on Discord that some people are asking similar questions, then I will try to explain it again. But I think for today, probably we can just have some questions related or comments related with what I said today to try to make it not. Sorry, my internet connection is unstable. So I think, so now can you hear me now? Yes. Okay. So sorry, I don't know where I stopped, but just wanted to say that, okay. So that I think we can have a few questions now, and in order to not making it really long, So we just revise if you have some questions, and if not, we can finish when you feel that you're ready. So is there any question?
Sorry,
Yes.
I missed a comment to Kevin because he's developing an atlas for.
Yes, so I said that's a great, but I don't.
Yeah, sorry, it was a message by Kevin. I replied to everybody. Sorry, and
okay.
Apparently a little bit sleepy still.
Okay, okay.
But that's great, Kevin.
Okay, okay, okay. So then I think there. I don't know if there are questions, but just let me confirm. So what do you think about today's class? And I would like people to say something. Is this that do you like this way? So it was clear or it was confusing you? So do you think, should I continue in this way, trying to keep everything on the screen, the script, the terminal, the plots, and try to cover things step by step? Or it was confusing?
First of all, Carlos Angeli here. First of all, this is a very nice attempt. Yeah, we all have been, I think, thinking of getting tutoring from someone, I think, and not many people are familiar with using Hsra. And you're explaining it in a very simple, followable manner. And yeah,
okay.
I found this very useful.
Okay, thank you. Thank you. Okay. I think Ivan was also saying thumbs up. So you also like it, Ivan? Okay, okay. Good. I think that also.
I think it's great, Carlos. I think you're doing a really great job.
Thank you. Thank you.
Yes, I agree.
Thank you. So, okay, so then just let me check again. Are you sure that you don't have any question or something that you saw and you said, oh, why he did that or something like that? Is there anything that you felt that was not so clear?
May I ask a question about the height scales in the model?
Yes.
If you have a pixel that you've inverted and you're looking at an optical depth and you see that the value of the height is, let's say, 70 kilometers, and then you have a pixel that is in another frame, and in that frame, the height is now 100 kilometers. Is it a correct interpretation to say that you're now viewing at that optical depth, 30 kilometers different?
Yeah. If I understand correct, so the idea is that we will work on optical depth scale. And the idea is that depending on the atmospheric conditions, the height where you have a given optical depth will change. So if you have a strong magnetic field, usually photons will escape from lower layers, but also with temperature and other parameters, things can change. So the idea is that the code will always work in the same optical depth scale, but the associated geometrical height to that optical depth will change. Also, it's important to remember that the geometrical height that you will have in the output in the atmosphere is computed under hydrostatic equilibrium. So in some scenarios will not be accurate. So you can trust in the optical depth and you can compare different optical depths. So you can assume that optical depth 0 from one pixel to the other pixel is the same optical depth, but definitely they will correspond to different geometrical heights. So
yeah.
Yes.
Also, the Wilson depression is not included. Then the 0 in the geometrical height is always in the log equal 1. Then if you have a Wilson depression, this is not included in the code.
Yes.
And if you, for instance, at running in a sunspot and you have a Wilson depression of 600 kilometers, then log tau equals 0 corresponds to 0 height. Then
yes.
the code does not include that.
Yes.
But even if it doesn't include the Wilson depression in terms of the values of the height scale, can you still consider the relative change?
Yes, that the code will consider that.
Okay.
Yeah. Mm-hmm.
Yes. Mm-hmm. Okay. Okay. Any additional question? comments? No? Okay, so then just let me say that today or tomorrow morning, I will send you the folders I used today, so you can run the code. I will send you a new version of the manual. There was a typo where it said that the geometrical height should be provided in centimeters. I think Ryan was the one found it, so thank you, Ryan. And it's in kilometers, so we already changed it, and now you will have a new one. So the geometrical height that you have or you will use in the atmosphere is in kilometers. Then I will also send you the new version of Hsra that is the same, but including the changes that Basilio made. I think it was Dave that had some compilation error. So this is now included. So I will send you this new version. It's the same, but just with those changes. So everyone can use the same. And then I will send you the draft of the, well, I think we can call it draft. So we sent the design paper yesterday. So I will send you the draft that we sent. So it was updated. We improved it a bit, mainly the language. So if you want to give it a second look, and you will have it. And also I will send you the updated version of design that this week there were also some compilation errors and we changed some of them. So then I will send it to you. Maybe if you have time, just run it again. And if some errors appear, then write them down in Discord so that we can keep improving at least the compilation part. So then by the time that we reach the design, everyone will have it compiled and working on their computers. Okay, so I expect to, so please wait for the mail for tomorrow, and let's meet in 2 weeks. Okay. So thank you very much. As I said, I am a bit nervous because it's a lot of people, so I feel a bit nervous, but at the same time I'm very excited because seeing everyone here, I think it's really motivated. So thank you very much, and I hope that with time I will be more relaxed and probably it will be easier to follow me. Okay, thank you very much.
Thanks to you.
Thanks, Carlos. Thanks.
Bye.
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 Thank you.
Bye.
I am sorry. Sorry
No,
for that.
it's okay. It's okay. It's okay. It's okay. Don't worry.
Bye.
Okay. Bye. Ciao. Okay. Okay.
Hi, few questions if you have the time, since I'm also using Hsra to do something else. Hi, everybody.
Yes.
So the first thing is, by the way, very nice workshop and everything. I really enjoyed. So
One second, Ivan. Shall I stop recording, right? Or do you want?
Whatever you want, yeah, but maybe yes.
I think I stopped.
It's not super related to